Okay, so let's start section 3 here of chapter 7. And in this section, we will see definitely some new stuff as well. But for the most part, probably section 2 is the toughest, with the moments of inertia in section 2 being something you do need to make sure you're comfortable with. So if you guys aren't comfortable with the moments of inertia, do make sure you go back and get more familiar with those. But if we're ready to move on, then with 7.3, we'll talk about rotational kinetic energy and then just kind of the conservation of energy using rotational motion as well. So a rotating body we know is going to have kinetic energy because the atoms are in motion, right? So if this is the center of mass and you have a whole bunch of atoms obviously around that center of mass in an object that may be rotating, right? Each of those objects as it rotates is going to have a linear velocity, and therefore each object is going to have some kinetic energy associated with just the fact that it's rotating, right? So this is something we did see in physics 1 as well, but how do we find that rotational kinetic energy? Well, let's just start with our normal linear kinetic energy, right? And I shouldn't call it normal kinetic energy, but it is our linear kinetic energy. And we know the equation for linear kinetic energy is 1/2 mv squared. But how does the linear velocity relate to the angular velocity? Well, linear velocity is simply the radius times our angular velocity, right? We know that from our uniform circular motion and our angular motion section beforehand, right? The linear velocity is just the radius times the angular velocity. So if I take that and I substitute that into this equation here, I've got, instead of my linear velocity squared, I have my r times my omega squared. So then when I do that, I've got 1/2 m times r squared omega squared. And the significance there is this mr squared portion represents the moment of inertia, right, for a single mass. So if we were focusing just on one of those particles, that would be the moment of inertia of that particle, which gives us then the general equation for our rotational or angular kinetic energy. So our rotational kinetic energy is 1/2 I omega squared. The good news about this equation is, again, it's exactly what we would expect it to be, right? Instead of mass, the angular equivalent of mass is our moment of inertia, right? That defines how tough or easy it is for something to accelerate angularly, right? Like mass does for our linear motion. And then the angular equivalent of velocity is simply our omega here, our angular velocity. So anyway, so this is the equation I've got. This is the equation I developed then for the rotational kinetic energy of any mass or any series of particles as well. Right, so once again, just like in section 2, the biggest task becomes, can we find the moment of inertia for the specific objects that we are dealing with? So as a quick conceptual example then to start us off in this section, right? So we've got a section of hollow pipe and a cylinder that both have the same radius, the same mass, and the same length. They both rotate around their central axis with the same angular speed. Which one has a higher rotational kinetic energy and why? Well, the y is just going to be focusing on the relationship, right, for the rotational kinetic energy. So I know my equation, my relationship here is 1/2 I times omega squared. Right, so if I want to find my rotational kinetic energy, I just need to find my moment of inertia, and I know that they have the same angular speed, so they have the same omega. So then all we have to do is think about how does the moment of inertia for these two compare. And hopefully that's something you guys are already pretty confident with going back to section 2. But if we want a quick review of that, we might as well do so. Right, so if you have a thin hollow pipe where the empty space here is obviously no mass is included there, and then I have a cylinder of the same radius, the same mass, except that mass is more evenly distributed throughout, right? If we just compare these two in general, we know that the moment of inertia for the cylinder is going to be lower than the moment of inertia for the hollow pipe. And the reason for that, right, is the moment of inertia over here is mr squared because all of the mass is as far away as possible. Whereas if we go back to section 2, we saw using calculus that the moment of inertia for a cylinder or for a disk like this, right, is 1/2 mr squared. Right? So since they have the same mass, the same radius, the moment of inertia for the hollow pipe is going to be bigger than the moment of inertia for the solid cylinder. So then if the hollow pipe has a higher moment of inertia but the same angular velocity, then obviously the kinetic energy is going to be higher for the hollow pipe. Right? So the answer to this is the hollow pipe has the higher kinetic energy, the higher rotational kinetic energy. And again, the rationale for that, it has the higher moment of inertia and the same angular velocity, right? So the higher moment of inertia, same angular velocity. So obviously the kinetic energy then is going to have to be higher for that hollow pipe, right? So a very conceptual example, not something we even necessarily had to calculate, but one that is important to once again find that distinction between the moment of inertia of a solid disk and a hollow pipe. Okay, so question 2 here is a good question for getting us to focus on kind of just the basic relationship for if we're just dealing with isolated masses. And what I mean by that, if you read through the question here, they say that we do have 3 masses, which obviously do have a significant mass, but then the lightweight plastic rods is indicating that the rods do not have any significant mass. So really, as we're rotating around this axle, we just have these 3 distinct masses, right? So it's a good question for us identifying that. So at what angular velocity does this widget, does this device here have? If it has 100 millijoules of rotational kinetic energy. So obviously for part A here, I'm just going to start with my rotational kinetic energy, which is 1/2 my moment of inertia times omega squared. Right, so if I look at this equation, I'm looking for the angular velocity, so I'm looking for omega. I know that it is 100 millijoules, so it is 100 times 10 to the negative third joules of energy. And so obviously if I want to solve for omega, I'm going to have to do something to solve for I, right? I need to figure out what my moment of inertia for this particular structure is, right? And that's where we do need to have the key understanding of how to find the moment of inertia for just discrete masses like this. So again, the nice thing for part A here is I'm not worried about the mass of any of those rods. So then the moment of inertia of this whole structure, right, if it's just 3 distinct masses, the moment of inertia is just the moment of inertia of all of those masses added up together, right? So if I want to find the moment of inertia for this object, I just need to find the moment of inertia for each of those individual masses and then add them all up, right? So I will maybe call this one mass 1, this one mass 2, and this one mass 3. So the total moment of inertia would equal m1 r1 squared plus m2 r2 squared. And again, I don't have to do anything fancy for like no coefficients out front or anything like that, because these are the entire radius away right from them. And then finally m3 r3 squared. Right, so as I go through here, just identifying how far away is it, and then what is the mass that I know. Okay, so the total moment of inertia equals mass 1, which I'm calling my 0.250 kilogram block, which is 8 centimeters away, so 0.08 squared, plus my second mass, which is 0.150 kilograms, and it's located 6 centimeters away, so squaring that. And then finally my third mass, which is located at the axis of rotation, right? So even though that does have a mass of 0.30, its radius would be 0, which obviously then kind of negates that whole thing, right? So the moment of inertia caused by that mass is going to be 0, since it's at the pivot point, right? So anyway, calculating then my total moment of inertia is as easy as just calculating these numbers here. And so when I do that, I get about 0.0021214 kilograms times meter squared. So that's the moment of inertia for this structure, and as soon as I find the moment of inertia, it's easy enough to solve this problem, right? So bringing that back together, I know my kinetic energy is, again, 100 times 10 to the negative third, which in other words is 0.1, equals 1/2 my moment of inertia, which I just found, 0.00214, times omega squared, and I now just need to solve for omega squared, right? So a pretty easy solve as soon as we get this set up, and we can find our moment of inertia. So solving for the squared, we get the square root of that, and it's about 9.67 radians per second. So the angular velocity here, the angular velocity of this system, assuming that the rods themselves are massless, is 9.67 radians per second. Okay, so part A, hopefully nothing too bad. I did throw in part B, and mostly because I do want us to think about this relationship here, right? So I did throw in part B. I'm not actually going to solve this all the way out. I think it's probably a little bit more complex than something they would give us, but I still do want you guys to think about how to approach this, right? So part B, what if the mass of the rods was not negligible or were not negligible, right? And instead they each had a linear density of 10 grams per centimeter. Now the biggest problem here in terms of working this would be this hypotenuse rod. So I'm actually going to go ahead and modify part B a little bit here and say, let's just assume that this rod and this rod did not have a mass, and we'll look at why here in just a second. Or excuse me, those two rods do have a mass and this one doesn't have it. So here's what this example would look like. And again, I'm not going to work all the way through it, but I am going to set this up. So the big thing that would change would be the total moment of inertia of the system. If I still choose that third block to be the axis of rotation, and then I have a rod extending this way with a mass at that end, and a rod extending this way with a mass at that end. To find the total moment of inertia, I would still add up all of the moments of inertia of each individual structure. Now the only difference would be, instead of just mass 1, mass 2, and mass 3 as I did before, right? So yes, I am still going to add those moments of inertia together, but in addition to that, I'm also going to add the moment of inertia of rod 1 and the moment of inertia of rod 2, right? So I might call that 1r being rod 1, and then 2r being rod 2, right? So that is something I would want you guys to be comfortable doing if we had to, right? To find the total moment of inertia of this system, we would still just calculate the moment of inertia for each of those masses individually, and then we would add the moment of inertia for the rods as well, right? So how would I find the moment of inertia for each of those rods if it's being pivoted about this axis of rotation over here? Well, that goes back again to last chapter, or last section. In the last section we said if a rod is pivoted about this endpoint, right, then the moment of inertia for that rod, we saw the equation, we actually derived that equation a few times, would be 1/2 ml squared, where m is the total mass of the rod and L is the length of the rod squared, right? So for each of my two rods, I would then do this equation as well. So for rod 1 here, I would do 1/2 mass 1 and then length 1, and then for rod 2, I would do the same thing. So for that second rod, I would do 1/3, excuse me, not 1/2, 1/3 m2 L2 squared, and then I would just add those into the moment of inertia as well. Okay, so we could certainly calculate this. We could find the mass by using the linear density and the length to find the total mass, and then pull that into play here and practice doing that. Again, the problem here with doing the third rod would be the fact that if this third rod is at an angle, not every mass is going to be the same distance away from the pivot point, right? So this would require a much more complex, it wouldn't just be a 1/3 ml squared situation. It would be a much trickier moment of inertia for a rod like that, where it's angled and my pivot point is somewhere like here, right? So that's why I went ahead and neglected the hypotenuse. But I would expect you to be comfortable finding the total moment of inertia for a system like the gray system that I had here. So anyway, at the very least for this problem, for part B, I would expect us to realize that as the moment of inertia goes up, what's going to happen with my angular velocity? Well, the angular velocity should go down, right? So the 9.67 that I found before, my second angular velocity should be something less than that number. So then to wrap up the first part here of the 7.3 notes, I'll just kind of recap on this, and then we'll pick up here with a few more examples in part 2. But anyway, the axis of rotation not through the center of mass of an object, then we know that that rotation will cause the center of mass to move up or down also. So what that's saying there is if I've got a rod, right, so if the center of mass of that rod is over here, but the pivot point is over here, then by rotating the rod, we're also going to cause a change in the center of mass, right? And the significance there is if the center of mass changes height, then I'm going to have a change in gravitational potential energy, right? So we're going to see a few examples that entail this, that bring this into play. But the big concept that we'll focus on then from here for the rest of the chapter is we're still dealing with the conservation of energy. So the total mechanical energy of a system is still conserved as long as there's no outside force, right? As long as there's no outside forces acting. So we know the total mechanical energy is conserved, and the total mechanical energy, we've seen that term a few times now. Hopefully we're comfortable realizing mechanical represents both kinetic and potential energy, the gravitational potential energy of an object. So the total mechanical energy would be the linear kinetic energy, the rotational kinetic energy, and the potential energy due to gravity, right? So U or PE, however you want to represent that. But several of these problems we're going to deal with now involve the total mechanical energy being, again, linear, rotational, and potential energy due to gravity. So we'll see some examples of how to work this in the next part of the video, but I will go ahead and stop here for now.